Mitch will discuss a novel approach to tracking unidentified aerial phenomena using passive radar detection. It works by comparing reflected radio and other common EM signals against locally known locations. So, Mitch, I'm going to launch you right into it, but I want to let the audience know you and I did an interview. You have gone on Coast to Coast AM. You have been part of the Galileo project. You have been in radar for like 40 something years. This is a real technology. This is like on my top 5 list of like technologies in general. So thank you so much. If it's okay, let me bring up, I think, your presentation, right?
That's it.
Wonderful. And I'll still be here. I'm going to mute myself and remove myself though. And thank you once again, sir.
Now, can you tell me how to move forward in the slides?
Yeah, absolutely. Absolutely. So if you put your mouse over the presentation, and again, this is because you uploaded it, you should be able to select the slides and you should have forward and back buttons. And just let me know. Looks like you have a video as well. Let me know when you want me to put that in.
Very well. Okay. Thanks so much for your introduction, and it's really an honor to be here.
Oh yeah, well, no, trust me, the honor is ours. It is again amazing technology. So,
okay, let me dive in. I want to talk about Skywatch, which is a passive multistatic radar network for UFO tracking. It was inspired by Peter Davenport. He wrote a paper about this in the mid-90s, but the technology didn't really catch up to where this could take off the way we want it to. So that's where I came in, and I started to work with, I did my first prototype of Skywatch working with the Galileo project. Let me just kind of blast through the slides here. I just put these in here as a kind of a reference point. Just keep in mind, this is mid-90s here, a bistatic radar receiver, and that's me. This is a again, early 1990s software-defined radio. So I was kind of at the beginning of that. And this software-defined radio that I'm holding in my hand is in this box here, making this bistatic radar doable. You know, at the time, a radar receiver was like a rack of equipment 6 foot tall. Okay, let me say, you know, if there's anything I'd like you to get out of this talk, it is that we're trying to actually get to citizen disclosure. So I don't want to just nerd out on radars or, you know, really, you know, or just some instrument that's cool or something. This is specifically for citizen disclosure. So in this talk today, I want to talk about what citizen disclosure is. And then I want to go through a top-down design for an instrument that obtains citizen disclosure, and out of it will fall these other things that we'll get into as they come up. So let's just talk about what citizen disclosure is, and you know, we can argue about it, but here's my definition, and I think it's pretty good. So it's really a mass consensus or a lack of controversy about data that proves non-human origin. And what's really important about this is if some scientific group goes off with some really cool instrument and finds some, you know, detection of something, okay, I don't call that mass consensus. I say one scientific group might be convinced. Or, you know, another example is, let's say that we all watch YouTube and we see David Grush get up and disclose reverse engineering programs or something. I don't consider that mass. It's mass, actually, but it's not consensus. There's controversy. So that means the president's not going to get up and talk about it. It means it's not going to end up in the New York Times because there's controversy. We don't know if it's true or not. So all of these little, you know, I chose these words kind of specifically to get to the point I'm trying to get at. If you get mass consensus, it means you have data that really can't be argued against. And it means everybody has that data. So it's a mass thing. So everybody can agree, yeah, that happened. And then also you want to know that data proves there's non-human origin. So that's what citizen disclosure is. Now let's talk about how do we design an instrument to obtain that. And I just want to let you know that, as Tim mentioned, as we started, actually my career is in instrument design. And there's some subtleties of instrument design that, you don't always think of when you look at what an instrument is supposed to do. And that'll come up as we talk about that. First of all, when you think about an instrument, you might think, oh, was it a radar? Is it an optical? Is it a magnetometer? Is it, what kind of instrument is it? But actually, I'm starting here. The most important thing about this instrument is the data is owned by the citizens. That is required because of our goal is actually to get the citizen disclosure. So we don't want to have the data holed away in either a scientific group or, in the military or something like that. We want it in our hands. And I'm just going to throw out there, what we're looking for is non-human made structured near Earth aerial objects. We could be looking for, undersea objects. We could be looking for something in orbit, but I'm narrowing this and for no particular reason other than there's an instrument that does this really well. So let's just say this is what we're looking for. And we know that there's been reports over the decades of crazy behaviors in the sky. And ATIP has kind of boiled that down to the 5 observables. Basically, it says that if you see an object do this, that's special. That could be an indication of non-human origin. But let's look at that, because debunking is actually surprisingly easy. And we don't want controversy. That's part of what we're trying to design for, the lack of controversy. Basically, if anything happens that you record that can be faked by a human, then it's been debunked. All we need is the possibility that something can be faked by a human. For example, a balloon has no control surfaces. A hypersonic missile goes hypersonic speeds, and maybe you don't hear a sonic boom. Maybe you don't notice, fireball or something. So, that's something that we can do. If you see something moving fast in the sky, it doesn't mean it's extraterrestrial. We have stealth aircraft. That's one of the observables, is low observability. But we can do that. We can even make hypersonic or supersonic vehicles that have no sonic boom. Things can fall into the water. That addresses, this idea of transmedium travel. Well, we could drop something in the water that could get on a videotape, and a debunker could say, well, something just fell in the water, big deal. The one thing, though, that stands out is instantaneous acceleration. When we see something that goes, let me see what my next slide is. Well, help me explain it. Now, let me just go back. When we see something that takes a right-hand turn at Mach 2, a right-angle turn at Mach 2, we know something's up because we can't even fake that. So instantaneous acceleration really stands out. Oops. And what we really want to do, specifically, I don't want to look for UFOs, UAPs, or something undefined. I specifically want to look for objects outside the paradigm of science. We really want to narrow this down to the characteristic, or an object that has a characteristic that we just throw our hands up, we can't do. That's what's important about this instrument, and this is exactly what we're looking for. So I just want to also separate this instrument, because this is a top-down instrument design. We're not just looking for something that's unknown or something we don't understand. We're specifically looking for something that's outside the paradigm of science, something that we cannot do, and that's really important. This is, again, what that thing is instantaneous acceleration. So here's an example. If you had some kind of instrument that showed you these tracks, and we call these kinematic tracks. So, it's a record of the position of an object as a function of time. If you see this object go in a certain direction, and by the way, Tim, can anybody see my mouse? Just asking.
Let me see. Try moving it again.
Yeah. I mean, I'm kind of moving it around.
No, they can't. They cannot see it. Okay.
Is there a laser pointer equivalent in this presentation?
I don't believe so.
Okay.
I am not sure. But
all right. Well, then I'll just talk my way through it. That's fine. If you see a track like this, where an object is moving in a certain direction to the southwest, suddenly it's moving to the direction of the northwest, you know, that the acceleration associated with that turn could be 1,000 Gs, 10,000 Gs. We don't know, but it's something that our airplanes can't do. When our airplanes, or when anything that we make goes Mach 2 and makes a turn, a 90-degree turn, it puts a radius on that turn and keeps those G's down to something below 10, so that either the instruments inside or if there's people inside, they don't get squished. But if we see something that doesn't do that, something that can accelerate in air with that kind of acceleration, that's just something we cannot do. That's an oops. That's an object outside the paradigm of science. Okay, now let's move on with this instrument. Again, I'm really trying to emphasize that this is an instrument that's designed top down to get to citizen disclosure. So I wanted to throw out this probability of detection. This is a graph from a book that Jacques Vallée wrote. And it's kind of interesting. On this lower curve, it says the sight distance. And on this, the vertical axis, we have the number of sightings. And we see this curve that goes up. So in other words, if you can see further, you'll tend to see more. There'll tend to be more sightings. This was taken out of a statistical database where people reported, what their sight distance was with each of their observations. Now it's kind of interesting. It says theoretical here. One of the curves is called theoretical. What does that mean? Is there a theoretical curve for how often we see UFOs? Well, there kind of is. It's related to the volume you can see. So therefore, if you can see 10 times further, you get the volume that you can actually see is 1,000 times greater. So that's why this curve goes so steep. It's the cube of the sight distance, essentially. So that's really important to know. And so by the way, this is a radar that I built, or let's scratch that. I worked on this radar. Many people built this radar, but I worked closely with this radar. It's a really high-end meteorological research radar. But if you notice, it's pretty big and just sits there. And one thing that we discovered was it's great to have these instruments that are very, very high quality and very, very sensitive. But sometimes, let's say you're searching for a tornado, what is the chance a tornado is going to come within your volume? So what we did, this is all at the National Center for Atmospheric Research. You may recognize these. This is a storm chasing truck. This is me standing in front of it. We decided that what made sense was to mount radars on trucks because we need to get that statistics up. So it's not good enough just to have a radar or some, whatever instrument it is. If the phenomenon never comes by you, then who cares? So what you need to do is drive to it. Or in this case, this is called the electrodoppler radar. In the back, there is a radar sticking out the back. Again, we flew to where the weather was. So we didn't leave it up to chance. And that's a trend in instrumentation nowadays. It's not just to have a good instrument, but to have a good instrument with a high chance of seeing something. So that becomes part of our citizen disclosure. Okay, oops, go back here. I wanted to compare, when you think about, let's find an object in the sky that's doing these kinematic tracks, how do you see stuff in the sky? Normally you immediately go to camera. Therefore we're gonna have cameras. The issue with cameras though, cameras don't give you range. And we run into this all the time when people are debunking, or with any video that you see that's been posted, there's always a question, well, is this a small, did somebody hang a hubcap from a string right in front of the camera, or is this 10 miles away and this thing's a football field size? So you don't have distance with a camera, so therefore you're unable to get pretty much everything on this list. You can't get distance, therefore you can't get position, therefore you can't get velocity, therefore you can't get acceleration. So if you can't get acceleration, we've missed our main point of, as we saw before, the one characteristic we're really looking for is that instantaneous velocity. instantaneous acceleration. So video camera is pretty much the same thing. It's great to see videos, but we always see a lot of debate about them, full of controversy. The biggest issue is nobody knows how far away it is. The only way to address that with some kind of optical instrument is to have triangulation. So that would mean you'd have to have multiple cameras observing the same thing at the same time. And then you could reverse using triangulation, you could figure out where that thing was. So now you have distance. And then using that distance, you can get instantaneous acceleration. But there's some other issues. One of them is the sight distance of a camera is really not very far, maybe 10 to 15 kilometers, let's say. If you have a wide field instrument, which is what you need in order to see the whole sky. But we go to the far right of this and we see that radar actually hits all the marks. The only one issue about radar is it doesn't show you what the object looks like. It just looks like a blip on a screen, but it doesn't show you the structure of the object, but it does give you distance. Therefore, it gives you position. Therefore, it gives you velocity. It's impervious to weather. There's many, many advantages of radar. And in fact, there's a monopoly. The government has a monopoly on radar data. And it's probably no coincidence. We don't really get to see radar data very often, if ever. It's so valuable and it's quantitative. But people don't necessarily want to have $1 million transmitter, a 1,000,000-watt transmitter that costs $1 million, at their house, or you don't want to buy that for your scientific instrument. Those and active radars, we normally call that, is expensive. So we're going to look at passive radar. Passive radar uses transmitters of opportunity, which means, hey, there's already things out there that are sending signals into the sky. And those signals are bouncing off objects that are in the sky. And the examples are FM radio, digital TV transmitters. In the case of FM radio, it can be the equivalent of hundreds of thousands of watts that are being transmitted and continuously in all directions. Mostly it's focused towards the horizons, which is fine. And there's some gain on it, so it's not exactly transmitting straight up, and that's fine. We can get around that. But it's a lot of power that we can take advantage of. And when you make a receiver for that, you don't have a big transmitter. All you now, and especially with the technology of today's, the software-defined radios, the receiver can be small, light, and inexpensive. That's really important, again, for the goal of citizen disclosure. Another bonus to this is if we did have a radar that did have the location of every object in the sky, then we can use that data to get people alerted. Let's say everybody had an app, and the radar could tell people, hey, there's something coming from the southwest. Run outside and look to the southwest and get ready to record. So we can associate an app, and I call this a bonus because once you have the radar data, you have a gold mine of information. Namely, you have where an object is and where it's headed and how fast. It could take a right angle turn and not end up where you want it to be, but that's fine. Maybe you can get several people to run outside and get optical video of the object from different angles, which is a multi-sensor input. So you can use that data to triangulate and get another fix on that position of that object in addition to the radar fix. So that's a cool bonus that comes out of this. So before I go on, I just want to summarize now. That was our little blurb on instrument development. And I want to really highlight a couple critical points. We're designing instruments specifically designed for citizen disclosure. What that means is, number one, the data has to be in the hands of the citizen. Number two, it has to be deployed in a grand scale because we want to get our statistics up. We want to look everywhere so that we can get the data no matter when the thing happens or where the thing happens. And then we get this bonus of the optical data. So what we're leading towards is a network of radars. So let's talk about a single passive radar receiver, which is the heart of this system. Here's a little image that shows you kind of the setup of the whole thing. So you have, in this case, let's just stick with FM radio transmitter. It's a kind of a beautiful signal to work with in this for this application. It's transmitting. There's a signal that comes from the transmitter and will hit your receiver. That's pretty unavoidable. And the signal also hits whatever's in the sky. Then an echo of that signal bounces off the object in the sky and hits your receiver at a little later time. There are certain cases when you are shielded from the transmitter. Let's say that you're in a valley, and the transmitter signal is pretty much going over the top of the mountains and not coming down into your valley. We can do another technique where we grab a reference signal from the transmitter and get that reference signal to the receiver. And in a little bit here, I'll tell you why the reference signal is so important. It's unavoidable, as I mentioned, but it causes a big problem, which I haven't mentioned yet, but it also is essential. A single bistatic receiver has pretty incredible, one based off FM radio, has pretty incredible performance. It can see objects out to 150 kilometers. And in fact, it can go much further than that. And we'll talk about that in a minute. We can see altitudes up to 80 kilometers. Now, some of these numbers I picked here have to do with the specific setting. So you can change some of the settings and change some of these numbers, but I'm just drawing a line in the sand. Here's where we're going to set up our receivers for this application. Altitudes up to 80 kilometers, so that's pretty much near the edge of space. Velocity up to Mach 6. Acceleration up to 2,700 Gs. So we can measure that directly, not by inference, but directly. Full sky observation. And we'll get kinematic tracks at 15 samples per second. So that means I showed that picture before that showed the green lines going across a map of the country. That means that the green line is actually composed of little samples that are every 15 times per second. And the data that comes out of it is quantitative and of scientific quality. And just to kind of highlight, there's some examples here. This thing will be able to see a bird within 16 kilometers, a drone out to maybe 30 kilometers, a 1 meter sphere out to 90 kilometers, a Cessna out to 150 kilometers, and an airliner, could be out at 280 kilometers. And this is in order to obtain a 10 dB signal to noise ratio on detection. And by the way, this isn't, this isn't like a theory, maybe this will work. These things are in operation. The bistatic radar has been around for decades. As you saw, I was doing a weather bistatic receiver back in the 90s. So this stuff is proven. It's not like it might not work or something like that. It's a done deal. This technology is there. The way bistatic works is, if you can see, there's a little house in that picture, and there's a little antenna in that picture. The little house is a receiver, and the little antenna would be an FM radio station. And between those two things is the direct path distance shown with the dotted line, and then something that would be in the atmosphere that's reflecting would the signal would come from the transmitter antenna, reflect off that, and make this triangle that you see in this picture. Now, it turns out that at one bistatic receiver, all you can measure is that delay. And that delay places that object somewhere on this ellipse, or really it's an ellipsoid in 3D space. And that's all you know right now about that object, is that it's somewhere on that ellipsoid. And also, a little bit about the Doppler velocity, which is perpendicular to that ellipsoid. So that's the information you know about that based on a single bistatic receiver. So keep that in mind, because a regular radar has got a much more simple geometry. It just bounces off an object, bounces straight back, and the distance is just 2r, an r going out and an r coming back. So let's look at how actually, Tim, could you play that video? There we go. This video shows the prototype system I did for the Galileo project. On the left here, and going horizontal, we have distance, and this kind of a bunch of dots that go vertically on the left there is 0 distance. And then going to the right is about 100 kilometers. And then the axis, the vertical axis, is the Doppler. Now, again, you can't translate this exactly into a position, even though it kind of looks like those objects, based on what we're normally look at, are, it's not a plan view of a map with objects on it. That's not what this is. But it does show you that the Doppler of each object and how far away it is. There's actually an airport that you can see in this that's right on the center line, because the aircraft are coming to 0 Doppler when they get to the airport. It's about 52 kilometers away. If we can go back to the presentation. Okay. So how do you do it? We have an antenna. We use something called correlative range. How it works is you receive your signal, but you have an idea of what was transmitted, and we call that the reference signal. So you have to know what was transmitted. In the case of a FM radio transmitter, we're not demodulating it into audio like a regular radar receiver or like a regular FM radio receiver works. What we're just doing is looking at the electromagnetic energy, and it's about a certain band. If you're looking at FM 96.3, you look at the signal that's being received at that frequency. It's basically a random phased jitter of a carrier. That's what the FM radio signal looks like if you don't demodulate it into audio. And from our perspective, it looks pretty random. A phase from one moment to the next is just all over the map. If we have a copy of what was transmitted, and then we receive an echo from an airplane, those two things at some delay, so we have to adjust some delay, then those things will match up. And we put that through a low-pass filter, and we get a detection. So I'm getting into some of the nuts and bolts here. It's kind of fun. But a way to think of that is, suppose that, suppose you take a test, a multiple choice test. It just looks like a bunch of random things when you just look at the piece of paper. But the teacher can take an answer guide and compare those and figure out, if you got the dots in the right place. But this problem that we have today with the radar is similar to having that, except you don't have any numbering on the answer sheet. And you just have a bunch of random dots that appear to be random dots. And the teacher can't line up the answer key with the test. But there is one particular alignment where all of a sudden the score goes from 20% to 90%. And that's how you can tell you're lined up. So this is pretty much how it works with the passive radar receiver. We try every delay, just like how the teacher would try to align the test in several different ways until they think it's actually lined up right. If there's an object at one of the delays we try, we will get a response, because the phases coming in, that random pattern of phases coming in, will match the random pattern of phases that we have delayed from the transmitter. So I hope that helps kind of bring it down to earth, kind of what's going on with that correlative range detection. And then there's some quirks to the whole thing. When we correlate for delay A, then signals of a different delay act like noise. So they don't just disappear. They're still in there, but they're just at a different delay. And it comes through as noise. This is on the right-hand side in that picture where it goes into the low-pass filter. A bunch of the signal that goes into the low-pass filters is just random noise, because it's objects from other gates, other distances, that are not correlating right with the reference delay that you're using for that moment. The direct signal from the transmitter to the receiver is what you use to know what that reference is, but there's a big issue with it. It's 90 dB greater than the echoes you're trying to receive. Typically, not exactly, but typically. And that's a 1 with 9 zeros behind it in terms of power. So that's a big number. And you do have to go through some maturations to get rid of that in order to get anything to happen in your receiver. And that direct signal, isn't lined up with the delays of the other gates. So that looks like a noise. And that noise raises the noise floor by tens of dB. So if you don't do something to get rid of that direct signal, you'll have no sensitivity in your system. What you need is an adaptive noise canceller. And how you do that is you take 2 antennas, you point one of them in the direction of the stuff you want to see, let's say point it towards an airport or towards some region of interest, and you point the other antenna at your at the actual FM transmitter. That really helps a little bit. At least it gets rid of some of that 90 dB. It chops it down to maybe 70 dB, but you still have a 70 dB problem. To address the rest of that problem, you use an adaptive filter echo canceller. So this is just a picture of one. I'm not going to get into the details, and you can look it up. And there's also papers on bistatic radar go through exactly how to do all this stuff. None of this is, like I said, none of this is unknown. It's all been done before. We're just repurposing it for this very specific application. And so the other thing is, if we want to have this as a network that, let's say many of these are fielded, we can't be having people steering antennas around, pointing them at the radio transmitter and pointing them at the area of interest. This all has to be done automatically. So we use an antenna array to do that, and we use adaptive null steering and beamforming to essentially digitally create 2 channels that we can do this processing with. And here's an example of a 3-element array. This is for the Galileo project. 6 of these were built and fielded in Massachusetts for the Galileo project. The processor is in this little box here, and you can see the 3 antennas. But the idea is it would do 360-degree null steering and 360-degree beamforming, so that you can get at least that first 20 dB of chopping 20 dB off of that 90 dB unwanted signal. And that null steering looks like this. So what you want to do is point. So this is a circular, a polar display of the power received from any direction, or the sensitivity of power looking at any direction. And so you want to take this null and point it towards where the transmitter is, but you can see that the reception at everywhere else is pretty decent. Maybe just a little bit of loss in all the other places, but right towards the transmitter, maybe a 30 dB dip. So that's one way. That's the first step in getting rid of that unwanted signal. Oh yeah, and here you already saw that other picture, but I just kind of repeated here, and here it has the label, so that's kind of helpful. You can see there's 0 hertz in the center. So this is, again, that display that shows you Doppler versus range. It goes from 125 hertz to minus 125 hertz and out to 120 kilometers in this case. Okay, so to get the statistics up, we want to make this in a nationwide network. And also, it's not good enough to have that display that I just showed you that says, bistatic range versus Doppler, because you really need to know position. You need to get the location of an object. Because our goal, just to kind of bring us back to ground here, the goal is to get those kinematic tracks, and the goal is for everybody to get those kinematic tracks, and multiple instruments watching that, and everybody observing that and owning that data and believing that data, so that we can get a citizen disclosure. So let's just go through how that works. Like I said before, if you have one receiver, you don't know where on that ellipsoid that object is. But if you have 2 receivers, then you can figure out at least a line in space that it's going to be in. If you have 3 receivers, it narrows down to 2 points on that line, and 4 receivers gives you 1 point. Let me just give you an example of what I'm talking about rather than just the words. So let's say a receiver on the left there. So there's one transmitter in this example, a receiver on the left and a receiver on the right. And they're seeing some object. And on the left, you say it's anywhere on that ellipse, and on the bigger ellipse on the left. And on the right, you say that receiver sees something somewhere on this squished ellipse on the right. But what we know, if that's the same object, they can only be, that object must be somewhere on that line where those two ellipses intersect. And they're ellipsoids, again, they're eggs. And they would intersect in a curve, probably an ellipse, in that other dimension that's drawn as a line here. So you know, just from two receivers, you can narrow down the position of an object down to that circle or that ellipsoidal line in 3D space. So what we want to do is make sure we have a grid where no matter where an object is, it's going to get picked up by at least 5. 5 is my minimum number. Even though 4 works, 5 is overdetermined. But you can see when you do that, you get 3D position, therefore you get 3D velocity, therefore you suddenly get the ability to measure instantaneous acceleration by watching how the velocity changes with time. And then if you get more and more detections, you just have more and more certainty that what you're looking at is valid, and you can get a finer resolution to it also. And in this case, you can see that if the radar if these spacings are 30 kilometers, which is a typical kind of spacing for this system, many of these receivers would be able to, probably every dot in this picture would be able to see the red dot in the middle that I've drawn there. So you would have a very overdetermined and very accurate and very indisputable detection if you got all those detections from all those systems. And the cool thing about FM coverage is it's everywhere. I mean, there are some gaps in here, but this is a map of the 60 dBmV radius of each FM transmitter in the United States. But actually, the radar is quite a bit more sensitive and can go further than that 60 dBmV line that you see there, or the curve for each one of those. So the nation is pretty well covered by FM radio transmitters, which is very cool. That means we can have a volume that is so huge that we're so far up on that curve that I showed you earlier that the chances of seeing an object become very, very high. In fact, if there's any object over the United States, we're going to see it. To cover the entire nation is, like as I mentioned, a 30-kilometer grid. That's about 10,000 radar receivers. That means that if you wanted to just have 5 receivers pick up something, none of them would have to see more than 44 kilometers. Those are all really good conservative numbers. If you got those detections within that range, you'd have high signal to noise ratio, very good accuracy on the measurements, and likely to be really overdetermined by the additional receivers. And here's what it would look like on the map, just to give you an idea. That's Minneapolis, just as an example, where the receivers would be in order to get this perfectly square grid. In reality, what we want to do is put a product on the market so that people can buy this and put it on their house. And we don't know where their house are going to be. And maybe in a city, there'd be 30 in a city, and then a few out in the country. So we don't, the spacing isn't going to look like this perfect grid here. But if we can at least get this as a minimum, so at least make sure that no point is any further away than this grid would allow, then we've achieved a pretty good goal. But some people have mentioned, I think Tim and I even talked about it on our interview, you don't have to have 10,000 systems out in the world for this to work. You could have 5, because 5 has a pretty good, pretty good coverage range. And you can get data out of that. If you're lucky, you might see a right angle turn. Okay, now another thing that's really important about the system, I have to just make sure I'm doing good on time. Another thing about this system is we do real-time calibration. It's very convenient to use aircraft ADS-B data. And if you're not familiar with that, every airplane, commercial aircraft and private, almost, let's just say a lot of the private aircraft as well, are equipped with an ADS-B transponder. These transponders ping their location and their velocity based on a GPS measurement So you can put a little receiver on along with the system. There can be a little ADS-B receiver that picks up all the aircraft in a pretty good radius and knows their exact position. So if we know the exact position of airplanes, the radar picks them up, as I showed before, quite easily. And the position of those airplanes, we can use that, the system will figure out where the position of those aircraft is and can compare that to the ADS-B data. So that is a really convenient and clever way, or cute way, of keeping the system in calibration, or detecting any receiver that might have any kind of problem. And it's kind of interesting because this would be going on 24/7. There's pretty much always airplanes in the sky every moment of the day, especially in this 150-kilometer radius. That's enough to see 100 airplanes at once almost every moment of the day. And those will all be being used as calibration in the background to make sure it's really calibration and validation, right? To make sure the system's working and none of the receivers are doing anything they shouldn't be doing. And if at the same time an object comes through that volume and makes a right angle turn while you're simultaneously detecting the position of all those aircraft and proving that those are correct, there's going to be very little doubt that that object that did that right angle turn, that measurement is also correct. So this validation turns this from a hobby thing that you can put in your house or whatever. It turns it into a traceable, calibrated system that can be used to reliably obtain, quantitative data. And that's a pretty awesome thing. And that's part of, again, we designed the system specifically from the top down to be uncontroversial in the data that it provides. When it shows something doing some, a crazy maneuver in the sky, there's not going to be a question whether that was an anomaly. That it's going to be pretty much a done deal. And, as part of this, there'll be a web display that's similar to what we've seen for these. There's flight tracking websites out there that show you a plan view of the United States. You can zoom in where you want, and it will show you, the aircraft that are flying around. The idea for Skywatch is the same thing would be available, except now it shows you, actually we would declutter the screen with all the known aircraft, so you only see the anomalous aircraft, but everybody would have availability to that. So if there is something that flies to the sky and does a crazy maneuver, everybody that's watching can see it, and there's no barrier between you and that data. The citizens own this data, and that's critical. Okay, and then this all boils down to the way to make this instrument work is to have this network, and the way to have a network is to have low-cost consumer receivers. So to get to the point where citizens can put this on their roof, there'll be a box that goes in their house and an antenna on their roof and a little cable between the two. That's as complicated as it gets. It'll be plug and play and very easy to manage in terms of, like, if somebody can install a printer, they can install the Skywatch receiver. And then the calibration that's built in will make sure that it's been installed correctly, because we'll be able to see if it's working correctly. What needs to be done to make this consumer Skywatch receiver is to develop a low-cost consumer receiver and develop now the hands-off antenna. That means an antenna that can electronically steer that null and the main beam, and develop the server backend that's going to be the interface, the user interface for people. Go through the development of the real-time calibration. And if you're an engineer or product developer, you might notice that nothing on this list is like make some magic occur or something like that. Nothing is everything here is just turning the crank on stuff that we already know how to do, but it has to be productized, and it really has to be productized to the degree that there's support, there's manufacturing, there's distribution, there's even marketing. All that stuff has to be in place just like any other consumer electronic product. And that's it's a handful of work, but there's nothing that's, we don't know how to do. I want to mention here, as part of this, there's going to be a few papers published in peer-reviewed journals that describe the system, just pretty much summarize or expand on the things that we just talked about today here, to describe the system, and also a paper that goes through in detail the error bars and when you do get an answer, how accurate or what are the limitations or what are the ins and outs of that? Because of course, as any instrument, there are definitely limitations, and those need to be spelled out in a peer-reviewed journal so that scientists know how to use this data. And that's important, by the way, because this data is critically useful to scientists. It detects, since the system, Skywatch system, detects exactly where an object is, now it becomes much more relevant for a scientific organization now to train their telescope on that thing, or train move their broadband antennas and point at that thing. So there's a bunch of narrow field instruments that can be vectored to the direction of the object, but you need to know where the object is before you can do that. And also, if there's some kind of hotspots in the United States or whatever that this thing detects, that will be a huge, important clue for groups with scientific instrumentation to go there and set up their instruments that will be less portable and don't have as much volumetric coverage as Skywatch. And by the way, nothing will have as much volumetric coverage as Skywatch because it's designed to cover the entire nation, which is part of the whole thing. So here's that box I was telling you. This is just an artist's conception. We don't have it designed yet. It seems like this is a very doable kind of configuration. It's not going to be so big. The antenna also is an artist's conception. It's not going to look like that exactly, but the idea is it's small and possible for someone to install on their roof, within the guidelines of HOAs and whatever. The status of it is right now, a proof of concept has been completed. So we saw the video I showed you. We saw airplanes flying in the sky. It has no trouble detecting those. We deployed the network in Galileo. We took a bunch of data. So there's a lot of data we can process to do some of the combinations and the actual position resolution with it. We wrote a peer-reviewed paper. I'm the lead author on that paper. It was in the Journal of Astronomical Instrumentation. And where we stand right now is we have scoped out the entire consumer product development. We know how long it's going to take. We know what the amount it's going to take, the funds it'll take, and we're fundraising for that right now. So, you can't buy one right now. That's not where we are. But we know how to make one, and we're looking for philanthropic funding to come through, because this is a philanthropic project. This isn't a big profit thing. It's going to make everybody $1 million. This is the cheapest possible receivers we can put on the market to get the broadest possible adoption of this, for a pretty narrow field. So I think we can get 10,000 products out there, but not if they cost $10,000. We got to keep the price down, and we got to make it really easy for people to use. And you don't need to have a degree in order to use it. It's just plug and play. So in summary, this is my last slide. The Skywatch passive radar UFO detector is designed to enable citizen disclosure. It is purpose designed to do that. And if you take anything out of this talk, that's what I want you to really get, is that if the object is citizen disclosure, which to me is, I wouldn't accept anything less, because who cares if we get some interesting, blip on just some other instrument. If you don't know where the object is and it doesn't resolve to a determination that that's an interesting object and it can be debunked, then I don't really care. But this instrument, Skywatch, that I just showed you, is specifically designed for citizen disclosure, because when we see those kinematic tracks with those right angle turns, or stopping and then going backwards or whatever, we have found something irrefutable. So that's my talk. Thank you very much.
Let me bring myself back in here. Mitch, thank you so much. I'm going to have them clap, but before that, what I want to do very quickly is, let me see. I want to share my Skywatch tab there, and that way people can see your website. I put the link in there. It's not showing the link. It's Ascendant ASCENDANTAI, ascendantai.com/Skywatch. And they can learn more about the project there. And I will scroll up briefly for them. Inspired by Peter Davenport. Again, I am so excited about this. And so I just want to like convey that to the audience. This is the real deal, right? Because a lot of the technologies that we work with are very theoretical, or they're in the rudimentary stages of testing, or we're testing ideas or whatever. What you have is, it is basically fully developed, right? And so that doesn't mean that it's out there in the market that people can buy yet, but what it means is you know that you can build it and it will be put together and it will work and it will help detect and track UAP, which is something that is desperately needed, absolutely desperately needed. So again, Ascendant AI.
If you scroll down a little bit, you'll see our interview.
Okay.
There you go.
There we go. Okay.
Don't miss that.
And I can drop I'll drop a link in there as well. Again, I love detectors, and one of the reasons that I love detection systems in general is because the bar is lower for success, right? You don't have to propel anything through space. You don't have to warp space and time. All you have to do is detect and track the signatures for something that is. But then the other part is this could give us so much valuable data, and there are, SETI at Home was one example of this, where you're kind of crowdsourcing, right? You have this open source network of people that are contributing to something larger, and Skywatch is perfect. I absolutely love this idea. So let me thank you for presenting, but I also want to, here, I'm going to, I will remove that. Okay. And I'm going to bring the guys in here. I think that's everybody that we have. Okay. Andrew's not there. Guys, let's give an enormous hand for Mitch Randall. Mitch, thank you so much. I don't know if it's coming through, but I'm like your number one fan, and you have tons and tons of fans out there as well. So,
well, thank you so much. It's a terrific opportunity to be able to present this and let the world know that this thing's ready to go. Yep.
Yeah, absolutely.
Can I ask one question?
Yeah. We don't have a lot of time, but go for it, Jared.
Mitch, awesome talk. There was one burning question in my mind for the whole presentation, and that's the engineerable data that we could get out of it. Is there any way that we'd be able to detect polarization changes, especially during maneuvers, especially triangulated, so you could see, oh, look, when we look at it this way, the polarization changes one way. When we look at it the other way, the polarization changes a different way. Now we can start integrating that information into our engineering ideas.
There's that, and there's several other things that I would say are kind of a next generation. The first generation doesn't have that. We're sticking with one polarization, vertical polarization in particular, which, by the way, in a bistatic radar, vertical is kind of the deal, because if you have a horizontal polarization and your reflection angle is 90 degrees, you might see nothing. So there's an issue there with the geometry of scatterers and polarization. But there's what you just mentioned, plus several other things we want to add to a second generation. But I'm focused right now on getting this out. This is important enough, I think, on its own. Great question, by the way.
Wonderful. Well, guys, let me wrap this one up, because we actually have a big presentation coming up. But again, Mitch, thank you so much. It is truly an honor, sir.
You're welcome. Thank you.